All right, so here under modules, right now, here at the bottom under 3D OpenGL programming, we have basically these videos, and we have also this zip file here, mesh model add-on. I've already got this zip file here, and I am going to extract it. I'm actually going to just put this, no, whoop, that was the wrong one, escape. This one I'm going to take and put inside here. First thing I'm going to do, I'm going to go here and I'm going to take models here. These are just some models that I made in Blender, just to have something to test it on. So it's object file.obj.mtl for the materials. So I just took a few there. I'm going to copy that, and I'm going to just put it inside here as well. Then I'm going to take my own version of the Control 3D program and just open that here. And then I have access to all of this inside here, so I don't have to go outside into the Windows Explorer. Make sure everything is running correctly. Yes. Nice. Okay, let's just close all of this for a while. So there are a few things here. Some of them we did in the last video, kind of changed in there, but I'm just going to go through all of the things that are in this mesh model add-on here. I've taken the models and put them in here, so I have them here. You can actually look at these model files, these OBJ files. This is a material file. It's just text. We can go through what all of this means later on. The object is this, and it just has these vertices and things, and then, you know, vertex lists and vertex index lists and all kinds of things. It's here as well. Okay, so we can go through what all this means, but it's a text file that just has all the vertices and materials and numbers and indices that we need to set this up. So the first thing I'm going to do, I'm going to take this Python file here, and I'm just going to copy that into my own project here. Paste it in here. So now it's just next to my Control 3D program and everything else. We can open this, look at what it does. Let's look at this load object file. The first thing it does is it references some class called MeshModel, which we don't have. So then we can go back into the MeshModel add-on here, and we can see that in base 3D objects.py that is here, this is not the entire base 3D objects py file that I have. It doesn't have the sphere or the cube, or we now have the optimized sphere, but it does have like my versions of vector and point. You can copy that if you want. It does have these imports here, the imports that we need or that are added. So I'm going to go into my own base 3D objects here. I'm going to copy these imports. So to begin with, we don't need any of the other stuff really. Like so, okay, so these are the imports I need. We might as well take point vector. Then there are two things I added here. The class color, which is just like a point, except it has RGB instead of XYZ, and material, which has diffuse, which is a color, specular, which is a color, and shininess, which is a floating point number. So we can take that and send it over point and vector here. You can also just take the entire file and you can take it over point and vector and down to cube if you want to keep cube. I have here sphere, optimized sphere, but I'm going to go below all that and just take the class mesh model and put it in there. You can close this and we can look at what we have here. So the class mesh model, it basically has all these different dictionaries so that it can basically look for different points or vertices or parts of the model. So the files themselves, the object file and the material file, they have these basically name identifiers, these string identifiers for what a material is called and for what a part of a model is called. So if the model has a sphere and a cube, or different parts of the model, each of them has a name, each of them has a reference to the material. So that's what these dictionaries do. These dictionaries are mainly just to kind of build the model. Once they've been built, there's this set OpenGL buffers. It does what we were talking about earlier. It makes buffers for each of the mesh IDs, basically. So for each of the mesh IDs, we make a different buffer, and then we load the data into that. And then we have the draw function that does similar things to our shader, to our sphere, optimized sphere, except it goes in a for loop for each part of the mesh. Anyway, so we have this here. Then inside here, this was base 3D objects, this, and then in the shader file here, we have this extra import for our shader. So I go into my shader here. Wait, I was going to have the other one open as well. So I go into my shader, and I add this extra import. I actually already have. Let's just leave it the other way around. This extra function here, which we made earlier, but you can just copy it from here now. And I'm going to see if we've done anything differently. Yeah, so we added this in this particular version, but that's just something that I'm doing here for my code. So you can copy this in, and it does, I believe, the exact same thing. And then it has changed versions as well of setting material, specular, and diffuse, because it's using the color. This is not something that's necessary to do. It makes it in many ways simpler to send the colors in from the material class. So let's stick to that. So I'm going to go in here and find set material, diffuse, specular, and shininess, and override them with these. So it's only this one and this one that changed, but we might get some errors now that we have to fix. But it doesn't matter. Okay. Let's go into shaders pie here. No. Let's take this one and close it. So okay, we've got in the models folder. We have everything from this file. We have what we needed from this one and this one, so I think we should be able to close this and continue. So close textures here. Yeah, so this is the models file where we copied it. Close this. And to begin with, see if after these changes we can at least get our program to compile. Probably won't. The main thing will probably be the color thing. So if I go in here, everywhere that I'm doing something like set material, I should be sending in a color with these numbers. So in the places where I'm just sending this in, this kind of seems like it's a hassle. I'm putting it into a class only to then take it out of the class. But after I have this model loader, probably most of the times that I'll actually be rendering models is through that, because it makes it so much simpler to make whatever model I want rather than use cubes and spheres. So in the end, since that uses this stores everything in these classes, then it seems simpler to do it this way in those cases. So I'm going to copy this, and then I'm going to find, I'll set material, some things, set material diffuse, that'll be color, set material diffuse, that'll be color, won't do it for the ones that are commented out. Okay. Okay, so this runs. Here I'm just using the optimized sphere. Fine. What we want to be able to do now is to say, if I've added all of these things, then I would like this to simply work. So the way this works, this is not actually a class in here. Instead, it's two files. One load object file and one load MTL file, which is the material. The load MTL file is simply called from within the load object file. So if we look at a simple model here, let's say simple box. Let's open both of these files. The box itself has these 8 vertices, which are the corners of the cube. It has these texture coordinates, which we are not using, but in the latest version of Blender, even if you don't put a texture on something, the object file that it exports will still always have the texture coordinates that it would use to texture map a sphere or a cube or whatever. So it'll have those in there regardless. But what I do when I read it at this point is I just ignore all the lines that start with VT. So I have these lines starting with V, one with O, which says, okay, this is going to be a part of the object. It's going to be an object within this model. So I call that a mesh, and I call the entire thing a model or a mesh model. So that's kind of just the terminology I'm using within my class. A mesh is this part within the file, but the entire model that is represented in the file is our model. So this particular mesh has these vertices, these texture vertices, these normals. Then it says use material, and before any of this happened yet, it did material library here, material lib, is in simplebox.mtl. So if I read this line, I call the operation load MTL file, and then we can see simplebox.mtl. New material means here's a new material. We can look at the combined one here. We can see there are more materials here. So there's new material called material 001. Has these numbers, one that's called, okay, this is fairly descriptive. Okay, so each of them has, NS is the specular exponent, which we call shininess. It's basically the exponent on Fung. So that's the specular exponent. This is the ambient color, Ka. Kd is the diffuse color, red, green, blue. Ks is the specular color. Ke is the emissive color, the emission. We haven't been using that much, but that's basically just a color that's added regardless of the light. And I don't remember or care about the rest. You can read up on that in the specification of the object files, basically. Illumination, this is kind of an ID for a particular type of illumination model that you then have to implement if you want to use this. I just decided we're making a simplified version. We care about ambient, diffuse, specular, or actually just diffuse and specular and the specular exponent. That's the only thing I'm reading from this. All right, so down to here. Positional vertices are V, VT are UV coordinates. They're just 2 coordinates. Normals, again, X, Y, Z. Use material. I don't remember what this does, and I don't read it anyway. Then F stands for face, which basically means a polygon. There's a face here. And in this case, because it's the cube, then each face has 4 vertices. But since I'm setting this up so that I only draw triangles, I actually have to make triangles out of those. So there's basically a check. If a face has more than 3 components, I basically read them like a triangle fan. Anyway, so each vertex is 3 indices. It's the index into the position list, the index into the texture list, and the index into the normal list. So it's always in that order in object files, which is not how I usually think it. I usually think it as position, normal, UV, but the object file is position, UV, normal. And another thing that we can't take directly into OpenGL, but the object file expects, is that there's a separate index into the position list, into the UV list, and into the normal list. So you can see these are always separate numbers. However, when we do this in OpenGL and we use the vertex buffer object, we have to have this interleaved. So each object is 6 or 8 numbers, which is each is a combination of position, normal, and UV. Which means that if we get the same index for a position, but a different normal for it, we have to take those two and we have to use them as separate vertex objects in our OpenGL code. Does that make sense? So we have to take every combination as a separate vertex. So they're taking an index into one list, an index into another, an index into another. We have to take these together and say each unique set of these, each unique combination of these 3 is a single vertex for us. I'm actually doing it worse in the current version. You could do it better. If they're repeated, I simply repeat them. So there will be repetitions in the way I'm reading it in now, but you can't fix that by, setting up a dictionary or something and checking for the combination you get every time. If I get this combination, I'm going to check if I've already gotten that combination. Then I'm going to make an index to that. So I'm not using indices. That's one more thing that we can do to optimize even more. We can set up vertex buffers and then send in a list of indices to read into them. Anyway, so for now, that's basically what this file does. If we look at the loading here, it's just a bunch of if sentences. It basically tokenizes each line. So somewhere here, I do tokens equals line split with no value on the variable, or no parameter, means that we split on white spaces. So I take each line, I split it on white spaces, so this line would become a list of strings where one string is just V, one string is just this, one string is just this, so on and so forth. And then I check token number 0. So if token number 0 is material library, I load material file with token number 1, which is the next token as its input, which is that file. If it's O, that means I'm starting a new object. That means I set a new current object ID. I print something just to see that I'm reading it. I used to do this. That is, say the current position list and the current normal list get new values here. However, here's an interesting thing about the objects. If we again look at the combined model where we have more than one object. So let's just search for this. So here, so first it starts with a cube. We have that. After that's done, we have another object, that's a sphere, and an ecosphere here, or icosphere here. So we have these 3 objects inside this. However, I have this vertex list that starts here, and it indexes into this. This is number 0. No, actually 1, 2, 3. That's another thing we have to do in our code, or I had to do, is that I actually had to do a -1 on every single index because it uses 1-based indices in the file, whereas obviously arrays or lists in Python use 0-based indices. So this one is number 1, 2, 3, 4, 5, 6, 7, 8. And that's what this is telling us. 1 will be this vertex here. 2 here as the first number. So the first face is 1, 2, 3, 4. The next face is 5, 6, 7, 8. Then there's 1, 5, 8, 2. So that's 1, 5, 8, 2, so on and so forth. You would think that when there's a new object here, then this vertex would again be 0 or 1, 2, 3, 4 in the vertex list that we have here. However, this is not the case. So we can actually see if we go way up here, that for instance the first face here is 9, 10, 11, 12. Because the vertex list that starts here on the sphere, so this is 0, no, 1, 2, 3, 4, 5, 6, 7, 8. Even if we start a new object that will only be indexing into its own vertex list, it still starts the indexing as if the previous vertex list is part of this vertex list. Does that make sense? So this one becomes 9, 10, 11, 12, 13, and up to God knows what, 500 something. So let's say it should end at 512, but instead it ends at 520. So then we have the ecosphere. So this one is 511 or 521, 522, 523. So it's a continuous indexing in each of those lists separately, position, normal, and UV. All right, now you know. But I went through the trouble of implementing this for you, so you can look at the code, you can understand it, or you can just use it. But I'm not going to make this video so simple that I don't try to force some teaching into it. Okay, so that's basically the idea of the files. This is how they're read. After they've been read, this is basically I'll add it to this mesh model, and it calls meshmodel.set OpenGL buffers. It's basically telling MeshModel, I've put all the different vertices in, I've put all the different models, I've put the materials and linked the different models to the materials. Now you can take all of those and you can set your buffers. So in base 3D objects here, we have this function here, set OpenGL buffers, and then it simply takes these. It has the vertex arrays are a dictionary. So each item in the dictionary is a vertex list, and the key is the name of the object that has that. So if we go back into just the combined model here, this here is the key. Ecosphere is a key to a particular model, and the underlying vertex list is the list of all these vertices. Or actually, it goes through the faces, and for each face, it makes a new vertex from this position and this normal, and it makes a new vertex for that in the vertex list. In the case of the cube, it'll actually make two triangles there. It'll take this and this here, and make a triangle, and it'll take this one, and this one, and this one, and make and this one, and make another triangle. And so it's not as optimized as it could be, because it always draws a triangle and it always completely triangulizes all of these faces, even though in some cases they're set up differently. But anyway, it's better optimized than it could be worse. So what it does then here is it goes through all the keys, these mesh IDs. It goes into the vertex buffer IDs, which is also a dictionary, and says the vertex buffer ID for this mesh ID should get a value from OpenGL generating a buffer. Then it binds that buffer. Then it takes the buffer data from the vertex arrays dictionary, which is an actual vertex array with this key, with the same key. It builds that, and then it unbinds. So it just does the same thing as the sphere, but it does it for every single mesh within the model file. Yes? So far so good? Then we call draw later, and it just goes through the same thing. It goes through all the keys, and it sets the material, diffuse, specular, and shininess from the material that we get from the material dictionary using the MeshMaterial key, and so on and so forth. And then we draw this same thing for the mesh ID. Yeah, so MeshMaterial is basically kind of like a link table, if you've done that in databases, like a double key. It's just a key table between the meshes and the materials. Anyway, so this draws it. My hope now is that after we've just, if you go to the beginning of the video, if you're watching the video, you can just look at the code I put in there. I'm hoping that we can now just make this work. And to begin with, see that this runs. Okay, fine. Now I am going to, where do we have sphere here? Okay, so let's take this. Oh, we can still load this though. Self dot object model equals. Now we should do. How did we import this? I guess we haven't yet. So let's import that then. Say import object 3D loading.
It's called OJB.
Here. That's not good. Let's rename it then. Oh well. I'll rename it later. Sorry. I'm pretty sure the files are OBJ though. Okay. So you can rename that. So we import this. I'm going to go here and say that's an JB underscore loading dot. What operations do we have? What's the operation called? Load object file. No, I'm not in the correct place here. Load. I was hoping this would. Okay, load object file. Alright, so it takes a file location and a file name because I use the same file location for the material file. It's simpler that way. So system.path0 just to be here, plus, and these models are inside the models folder. Models. So that's the location. The file name, let's just do metallic sphere.obj. Metallic sphere.object. Okay, let's at least see that it manages to load it. It does. Now let's take this object model, self.object model. Let's go down to where we draw, and let's just take one of these spheres. Okay, so this is all of the spheres. Let's not this sphere here and draw the object model instead. It should just be interchangeable like that. We just call the draw function on that, and there it is. So it's a different type of sphere, right?
It's a disco ball.
Sorry?
It looks like a disco ball.
It looks like a disco ball because it's flat shaded rather than smooth shaded. You can go ahead and read some other file in here instead. We have, that was metallic sphere, smooth sphere. It's just different models here. All of these are just one mesh within the folder, okay? Different color. Other than that. Okay, so I want to do one thing here. You can see how this specularity isn't that nice looking here. I think we can fix that in not a very optimized way, but a nice looking way if we just go into the both the vertex and fragment shaders. I'm going to go into, why is there so much stuff here? Let's close some of this. Okay, so the vertex shader here, we are normalizing the normal, and then we're sending it in here. In the fragment shader, we are just using them directly, but I'm going to see if we can say float s length equals the length of v underscore s. So I'm going to take each of these and actually do the full calculation. And normal length, and then take this dot product here and actually divide it by, this was s and n, so n length times s length, and this one, that's normal length and h length. Let's see if we can make it look a little bit juicier if we do the actual calculations. Did I forget semicolons? Python having a bad effect on me here in my C programming. Something else that I'm doing wrong here. Warning, 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 where are errors? Vn doesn't exist. Yeah, that's because it's called v underscore normal. That's better. It's kind of a juicier specular point there, right? And so now when it's actually smooth shaded, it is smooth shaded. We can't see, you know, that it's just made up of different polygons. Except if we look at the edge here, we can kind of see that there are corners there. But still, smoother. And on all the other ones as well, we can see these smooth, juicy specular points. Super nice. All right, one more that I'm going to add here, or not add. I am going to go into the original program. I am going to load what was called, I think, combined model. Or maybe we should make one instead in Blender. It's maybe nice to see how we export this to get these files in Blender. It'll be more exciting as well to see a model that we make ourselves here. Okay, so this is still a smooth sphere. Let's go into Blender. I'm pretty sure on this particular computer I just have the latest version of Blender. I used to need to think about versions because there was this third-party exporter for this specific like XML and text-based type, but it's much simpler now since we're just using OBG, which is a common thing and exported through most things. Okay, so Blender is fairly complicated to use if you want to use all of the stuff that's in it. So I'll just show you how we can do fairly simple things because I don't know much about using it, and I'm not really worried because this is not where I do my work. However, what we at least have is, if you look up here, you have a scene collection, and you can look at things that are in our scene, and the main things we're interested in are the geometrical things here. The camera is here as well, and light and things, but those don't get exported into the object file, only our geometrical things. So I have this cube here, and the first thing I want to do is just delete that, just to start with a clean slate here. If we want to add things, and this is actually, it's a different layout from when I used Blender last, the newest version that I got like just last week, it has things kind of in different places. So if you're using an older version, things might be in different places. But here we have this mode, and in this case we can use object mode is the only way because we don't have an actual object. We can change this later on, but we can go into add. There we have different things. Mesh is the main thing I use. So we have cube here, which is a three-dimensional object. We have UV sphere, which is like the latitude-longitude sphere. We have ecosphere, which is like a 20-sided die. We have a cylinder. We have a cone. So we have these different things that we can add. There are shortcuts to kind of in here clicking things and rotating things and doing things like that. What we can do though is we can go into the cylinder, we can choose the cylinder here, and under this we have all these different tabs. One of these tabs is the one that we're in, the object context. We can basically move the X and Y coordinates, just the location of the object. Here, this can all be done like in the program as well. Blender uses the Z vector, the Z dimension as up-down, and the Y dimension as towards and away from. Whereas we and OpenGL and everything that we've worked with basically thinks of it flipped. So we think of Y as up-down and Z as closer and further away. I think the base OBJ file converter like flips this by default, but I think you can set it so it either does or doesn't flip. Okay, so we can scale it in each dimension here as well. Oops. Scale it in Z. You can do things like this. You can just go through this. That's one thing. The main thing I wanted to look at is the material. So here we have the material, we have the cylinder, and there is no material as of yet. So we have to add a material to each object to make sure that we have a new material. At that point we have this. You can take the base color, choose a new color. If anyone knows Blender better than me, the version I used to use, the color would show automatically in this user perspective view. Right now, there's some setting I have to set so that the actual color, the material color, is the color that's used here. So base color for this, and then you can, specular, how much specularity there is, specular tint, so on and so forth. I think it's basically going from white or grayscale towards the color of the object. You can go ahead and try out things with the materials here. Anyway, so now we've set a material to this. So the cylinder actually is here. It has a material. You can give the material a new name as well. So cylinder material. All right, then we can go here into, so we choose the cylinder. So this is object mode. Sculpt mode, I think, gives us a way to kind of just stretch things. It's actually more interesting on a sphere. So let's go back to object mode. Let's add another one, a mesh, and a UV sphere. Back into this, let's just locate it a little bit to the side here. I want to scale it up. Well, in all dimensions, thank you. There's some way of locking this as well. You can use these locks here. Oh, well. Anyway, so we can size this up. I'm pretty sure if we go into edit mode, not inset faces, isn't there a way to make more faces out of this? Is there anyone here who is smooth, flatten angles? No, has more. No, basically, I'm thinking about kind of triangulating all of this, kind of dissecting it, getting more. I'm wondering if that's in sculpt mode. Simplify. Oh, this is so different from what it used to be. Anyway, what we can do here is, where's the blob or grab? Oh, that's a bit much. So there are different ways of kind of adding things to this. It's more fun if you have more polygons in it. It's so few polygons. I kind of wanted to split it up. Paint. Is there no kind of polygon split here? Inset faces. I don't know. I'm not going to do too much of. All right, undo that. Lots of things that we can do. Nudge. I can push them kind of to the sides. Anyway, this looks weird enough as it is. So at least, you know, whatever we do here, you can be pretty sure that you can twist it or it's a bit much as well. Oh, never mind. Okay, so you need tutorials on using this. At least we have, so if we go back into object mode, go back into new, add mesh, cube. Okay, let's select the sphere again. Sphere, let's put a material on it. So new material, and let's call it sphere material. Some base color on it. Let's make this somewhere around here. Let's take the cube as well. Let's put a material on it. New material. Cube material. And I have just a red color on that. Okay, so this is going to look super weird. I wonder if I've kind of ruined this sphere to begin with. I would still like it to be a usable object. So let's take the sphere and delete that. Object mode, add mesh. Let's put in another UV sphere. This is probably so much easier for people who actually know how to use this properly. Let's take it outside here, take it a little bit up. Fine, let's have it there. Let's scale it up in all dimensions. Something like that. Let's go into Sculpt Mode and just do some little changes, just so that we definitely see them when we look at it. This isn't quite gonna cut it. Not smooth. Layer, what does that mean? Okay, now I at least see that something is happening. It's some kind of weird sculpting project that I'm doing here. Fine. Let's do a little bit on the other side here. On the bottom. Stretch it out over these. Alright, fair enough. So now we've got something. I am going to take the sphere and make sure that it has a material. Just use the sphere material that we made earlier. So the sphere has a material, the cylinder has a material, right? Cylinder has a material, the cube has a material, everything is separate. Alright, fair enough. So I've made something. You go and make more interesting things, or what's even more interesting, go and find models, load them into Blender, then export them as OBJ files, and you've taken any model from the whole wide world or the internet, and you've made it something that you can now export into your program. So great. So at least just make sure that everything has a material here, and then let's go into export. Export. So wavefront.obj. That should do the trick. Let's call it blob and cylinder .obj, and this is the worst thing about Blender. It doesn't save the last location you saved in. It makes you find it from scratch every single time. All right, save it here. Export OBJ. And then I'm hoping we can go in here, we can look at our models folder, and blob and cylinder will be here. Okay. So we will take blob and cylinder, go in here, and we'll say that's what I want to load. And now fingers crossed, we will get our blob and cylinder into our program. It's there.
It even has the colors.
It has the colors, and I'm just going to go ahead and drop the whole. Wait, where did it? Here. This. So we can see that it's there. And it looks like it was supposed to look. Fair enough. Another thing actually that we can do, we can go in here and we can take the sphere, and I'm pretty sure isn't there something, if I go to edit mode, can I force smooth shading on it? I'm not sure it happened. So I selected it here, sphere, or this sphere here. Now I want to smooth the edges. No, this is not what I'm looking for. There was some way of doing this. Shading. Well, this is a little bit more complex than I was looking for, but isn't there something that's just flat versus smooth shading? Never mind. You should be able to find that, and then you can actually make the vertices be smooth shaded rather than flat shaded. And it's actually better optimized that way, because then you have one normal for each vertex rather than different sets of them. This is just way too complex to use for a quick demonstration like this. In an earlier version, I used to be able to find just smooth shaded. Not so much now. Anyway, layout here. But you can see it's on the other models that I was loading anyway. All right, so we have this. So we can load these models fairly simply in, but they won't have textures. But what we can do now is we can go into our base 3D objects, and we can look at our optimized sphere here. And we can kind of look at how we can add the texture coordinates, the UV coordinates, to our interleaved coordinates of with the position and the normal. Yo. Object shade smooth. Let's see if that's there, or if that's a help site from an older version. So as it go to object, shade smooth. There it is. Okay, fine. Now I have smooth shading on this. And if I now go ahead and do File, Export, Wavefront, export it as the same thing. should be able to go here, run this again, and see if the file has updated. And now it's smooth shaded. Cool, thanks. So, did we stop drawing the boxes, or did they just stop appearing for some reason? Or the cubes that were there in the background? Oh, they're still there. Okay, so they're still there. Why did they suddenly disappear when I started moving? Are they somehow inside this blob? Go here into display, where we're drawing the object model. Just go back into sphere draw. So there are the cubes. Okay. All right, so we want to get the textures back on those. So let's go ahead and see what happens now if I go into shader here and say, let's use textures. Well, start in that case and see what this does to the cubes and to the spheres. Okay, so we're using textures on the cubes now. Okay, so I want to, number one, I want to texture map this sphere. And I'd like to get a little bit of input from you to how we do that, and in the same time we can kind of learn a little bit about how the texture, about how the sphere itself works. So I'm in the wrong file here. All right, so let's just look at the optimized sphere here. So for every single vertex in our vertex buffer object, we are twice putting in these same coordinates here, using sine and cos of the stack and slice. But if we kind of stop worrying about the 3 dimensions here, and just worry about the 2 dimensions that we're kind of running through here. So we're going stack count up. We're going from the bottom, and we're going up. That's our outer loop. We're starting at the south pole, we're ending at the north pole, right? For each inner loop, we're basically starting at, let's say, Greenwich, and we're going the circle around and we're ending back there, right? I'm going to see if I have a texture here. Yeah, Phobos. Cool. Mars's moon Phobos is a nice texture we can use for this. Okay, so the question is, if I'm at some point in the outer loop where stack count starts at the south pole, ends at the north pole, and at some place in the inner loop going around, like what are the coordinates that I want to point at the texture?
Going from 1 towards, no, from 0 towards 1 in the UV space, and then either from left to right.
Okay, so basically the V dimension, the second dimension, we want to change in the outer loop. So if we go ahead and say for each of these, I'm going to do vertex array. Wait, this is tricky. No, this is not tricky. Let's just add a full vertex, then we'll just interpret it correctly later. So we're adding a... No. Vertex array is just numbers, yes. Okay, so we're just adding floating point numbers. So for these two, we've added 1, 2, 3 floating points for the position, 1, 2, 3 floating points for the normal. And now we're going to append first one for kind of the x or U dimension. Let's look at that later. But we're saying the outer loop. Oh, let's copy this. The outer loop is the second one. That's basically going from South Pole to North Pole. So the outer loop goes from starts stack count at 0 and goes up to stacks. But we want to go from 0 to 1. So how can we set something up here that will be 0 when we're in 0 and 1 when we're at stacks? Okay, a ratio between, so stack count is 0. So we can say, okay, stack count is definitely 0 at the beginning. Stack count. Yeah, static count. It's basically a ratio, like how far are we along? Whoa. Divided by how far do we need to go to be fully there. So that's stacks. Stack count divided by stacks, fine. And since we then put in another where we basically go stack angle plus stack interval, this basically means we're going stack count and then we're going stack count plus 1. So every time we basically need to be working on two latitudes. So if I'm here, I'm going around this latitude. I also need to be working on this one because I have to put the vertices in like this. Then in the next loop, I'm working on this one and this one, doing this. Then I'm working on this one and this one. So yes, I'm doubling all these vertices. Just going to have to deal with that. Sure, but I'll use a better marker if I need to make a better image. So for this one, we set up stack count divided by stacks. For this one, I'm going to set up stack count divided by stacks plus 1. And we know since, stack count plus 1 divided by stacks. And since we know that stack count will go from 0 to stacks, because that's what range stacks does. From 0 to stacks minus 1, that means the last loop here will have stack count plus 1 equaling stacks exactly. And that means our last loop will end at the top of the world at exactly 1. Fair enough. How about the other one? The other loop is from slice count in range slices plus 1. So I guess same thing. Except the slices are always used the same. We're not going forward with those. So then we simply say slice count divided by slices. And down here we just do the same. Slice count divided by slices as well. We don't need the plus 1 there. The plus 1 is only in the 1 dimension. Okay. So now we're appending more stuff to this vertex buffer. I'm pretty sure this is going to look like hell. Well, it's pretty cool though. But you get it. We've stuck some numbers into our vertex buffers, but we haven't really accommodated for how we're going to use them. So it's just using those texture coordinates as parts of those triangles. This is actually insanely cool. Especially if we had an animation on this, if you could kind of crack the code on how that works and kind of animate it from an actual sphere up to that. Yeah, and this specularity here just looks like pure energy here, some kind of fire. I like this. So do wrong things and see what they look like, and maybe they'll give you ideas for doing cool things. All right, but we have to accommodate for this. How do we do that? Like, where do we do this? We're sending a buffer array in here. We have to accommodate for this in how we tell OpenGL to read from this, right? Yeah, sure. So we need to accommodate for this. Yes, right there, in how we tell OpenGL to read from this. So where do we do that? Basically do that, yeah. When we draw, we set the attribute buffers. So we kind of need to go now into shaders and say, what are we doing now? Now, when someone is calling set attribute buffers, and we could actually make a different version of that right now and call it with UV, because our OBJ model loader is not using textures, but it's using the same function. So let's make another one that's called with UV, and in here we'll say that our optimized sphere, we'll call that one. All right, so now we're saying there are UV coordinates involved here. That means we are going to steal this here. All right, so we're setting position location, we're setting normal location, and we're setting UV location. So UV location will be reading 2 GL floats. Question is, what's the stride? The same as for the other ones, but the stride has changed, right? We now have how many GL floats rather than 6 for each vertex? We have 3 for position, we have 3 for normal, we have 2 for texture or UV. So we have 8. That was certainly elementary math, but it's not really the math that matters here, but understanding that we now have the UV coordinate as part of this. So each vertex object, each vertex that we read is now 8 floating point numbers rather than 6. The offsets. This is still offsetting from 0. This is still offsetting from 3. That is, after 3, we start this one. The last one, where is that one offsetting from? 6, yes. We read the first 6, then we read this one. So this would possibly work. Okay, so we've got it back. But we're not using textures, right? But at least we've made sure that we've stuck some extra numbers into our vertex, and we've told OpenGL to read the other ones correctly. So it's not everything is going all over the place. Now we are, however, going to say, well, in here, we're definitely going to put add textures to this. So we can actually see what happens if we just run this now. Interesting. It's the dice texture that's on it. But that wasn't really the texture map image that we were imagining for this. So we need to add, well, we've basically done everything we need to texture map the sphere. The only thing now, we need to make sure that before we draw it, I'm using the correct texture. So how did we do this again? Okay, yeah, okay, so we already have this one. Self texture ID Phobos. Where am I drawing the sphere? Is it here? Where am I drawing the cubes with the textures? Okay, so here we have this stuff. So GL active texture. Okay, fine. Let's take this. Let's put it before we draw the sphere. Did we then take the active textures off here? No, we just added another one. This was the dice one. Yeah, the other one had some specular map added to it as well. Let's go through what matters here. So we don't really need the specular map. We don't really want the specular map. So GL active texture, bind texture. I would like to go ahead and bind this texture. Can we bind it to none? Or, in fact, probably have to do it in our shader. Because in the fragment shader, we just have one thing here that's saying using texture. and then it uses both. Maybe we should have one switch for using diffuse texture and another for using material texture. What I am going to do is I'm simply going to take this line out, so we're not using the specular texture. Simplifies matters a bit here. So in here, we don't care about texture 1. Shader set diffuse text 0. Okay, fine. We'll just set it like this. So we're saying texture 0 is the active texture. We're going to bind that to this one here. Bind that to a particular, oops, here, to a particular texture image that we've already loaded. We've loaded it up here in this load texture function here. We went through that last Monday. And yeah, here we call it. So set diffuse texture on the shader. I think this should probably be all we need, right? Looks like the correct image. Maybe we should actually go ahead here, take the specular texture map just to see what it looks like. And actually add it again and go back into the fragment shader and actually use this. See what happens. Okay, so we lost the specularity. Okay, the specularity is kind of happening some places but not other places. It's a weird effect. What would be really cool is to do something like take an earth texture and take a separate image that is black everywhere where there's land and white or grayscale everywhere where there's water. Does that make sense? And then if you load that as your specularity texture, then you'd have specularity on the water, but you wouldn't have specularity on the land. Things like that. You can do super cool things with this. But now we have an actual spherical map. It should be really simple to do something like going here and saying earth texture PNG, fine. Just do an image search. This is a bit big. Why aren't any of them like in regular? Oh, this is a power of 2, right? Let's take this. Let's see. Wonder if we can download this one. How do I just do download image directly? Then I go onto the page where it's at, and I didn't actually get the image itself. So I'm kind of hoping, can I just save image as?
It's really small. It's just
The thumbnail. Yeah, there were a bunch of textures. If I go on the site itself, I can probably find it again. Here's Earth, 2K, that's enough for us. Let's do download on that one. Okay, fine. Save image as. Yes, somewhere in here. Programming sessions. This. Textures. No. Save. Right, it should be in textures now. Can I somehow copy the text? Maybe like this. All right. So we are are here. Should we make a separate one, or should we just... Ah, yeah, let's. Earth. Yeah, you can have a day map and a night map, and then you can, in your shader, kind of smoothly gradiate between the day and night maps, rather than just have have the light affected in a way that not only does the diffuse on the map that you have, but actually use Lambert to switch between the day and night map. So then you're using two textures and you're using your lighting calculations to switch between them. That's super cool as well. Still running this.
You have like the night lights.
Yeah, so the night map is kind of dark, but with all the kind of electricity lights and stuff like that on it, whereas the other day map is like the one that we have here. So instead of just having the day map on one side and black on the other side, you'll have the day map on one side and the night map on the other. And in your shader, you basically use Lambert to take the value from one texture and the value from the other texture and do a linear interpolation between them based on your Lambert. So a Lambert of 1 will give you full day map. A Lambert of 0 will give you full night map. But you'll always just have the color, render the color entirely as it is. You won't actually attenuate the color with the lighting, because then it'll disappear. Instead, you'll have the color always full, but you're just changing the color from one side to the other side. Anyway, food for thought and interesting to implement for those who are such inclined. Somewhere here we had Phobos here. Let's do Earth now. Okay, so we have an underlying color on this as well. It's maybe the reason it looked so weird earlier. So let's go into specular color. Oh, this is light diffuse. Material diffuse, yes, is very much yellow. Shall we try the C specular map? Okay, so you can see how the specularity works here. It's kind of these dots that have different specularity on it. Spastic motion. Okay, we can put a little rotation on it. So we can go in here before we draw the sphere. We can do, so as the last thing we do, number one, I'm going to flip it because the south pole turned down. And I'm going to go ahead and do self dot model matrix add rotation. Oh, okay, it was add rotate y on the other one. So we had it there all along. Add rotation y. Yeah, that's fine. It's going to be really fast. Yeah, self dot angle times 0.2. Okay, so now I can see it spinning. And now we can go ahead and see if we can find Earth here. Yeah, that's cool. It's probably, is it on the same one? So yeah, we want this one. This is a bit big. Can I get it smaller? Oh well, let's see what happens if we take a big one like this. Okay, cool. Save image as. Wait, this isn't the same place. Yeah, it was JPEG, of course. Water 8K, fine. Let's just copy this so I have that. Save. Let's go in here. So to begin with, let's make a new one here. Okay, so that's water 8K .png. Let's call it earth water or earth spec. Okay, fine. Now we go down here. Texture ID earth. Come on. Thank you. Just see if it works. So this is what that looks like. Oop. So specularity works on the water and on the rivers and on everything like that in between. It's cool when the Amazon goes past. Right, so interesting things to be done once we have control over the shaders and control over how they work and things like that.
That's like a numerous? Yeah.
Yes. So I should probably, yeah, okay. Probably because I flipped Y. Okay, we can fix that by, instead of flipping Y, we can add a rotation around Z by 180 degrees, which is pi. Is making more sense? Yes.
It'll probably go better if you reduce the shininess.
Sorry?
I think it's a bit high shininess for a giant body of water.
Yes, definitely. And anyway, when viewed from space, you're not really going to get a different specularity like that from it. You have the atmosphere in between, you have all these different things. So the actual surface that reflects things is kind of the same regardless, but it's fun to do these experiments anyway.
And the atmosphere's ambience.
Sorry?
Are we going to add atmosphere as the ambience?
As you could also do the same thing I was talking about earlier with kind of the texture blending, like adding the atmosphere on top of the diffuse texture and blending them together. I don't know. Or you could have two diffuse textures and you can kind of make one. The atmosphere should still, it should be only the atmosphere where that is, where there are clouds, but none of it where there are not clouds. So you can also do things like that. Make sure, you can just imagine what the calculations are and then put them in your shader and it'll work. It's the fun thing. Once you've started getting these things to work, you can just do these little things, add in more textures, blend them in any way you like. Just check if there's a color here, or if it's black, then I'm going to use the other one, but if it's not black, then I'm going to overlay it with this one, so on and so forth. Or use alpha maps for something like that. Okay, so now we have this working. Should we see if we can get texture maps from the... No, I'll leave that up to you. So, at this point, we start wondering, what if we add a texture to this? Fine. What happens if we add a texture to this is that the file that we get, models here, blob and cylinder object, that these VT lines will actually mean something. So you're going to have to read those as well. They have two numbers and you're going to have to add them, and we'll just add them to the end like all of the other ones. You'll have to read that in, and for every one of these lines, instead of me now just looking at this one and this one, I can show you where I do this. In the mesh model, when I'm adding a vertex, So, no, it happens in the loading, sorry. Object 3D loading. So if it's a VN, all of this, I'm just adding it to a local list that I have here, on position list, normal list, and I'm not adding, so you do the same thing. For VT, we'd append to some UV list a point or a vector. Doesn't matter. You need just the two numbers, the third number would not matter. When, however, we get an F, then we basically, okay, then we go through those, and I split the next token again. So I do tokens F. So I get each of these tokens. So the token number 0 is F. Then token number 1, 2, and 3 are definitely on this format that you can see. These always disappear. That we can see here. So the first token is this, the next token is this. So I take each of those tokens and I split them again. I split them with the slash as their splitter. That means I can take this tokens number I, and I can say tokens number something, tokens number 1, number 0 is the position. And if you go back here, tokens number the same thing. So number 2, that's the third split. So token 1, 0 and token 1, 2 are here. This one and this one. This one and this one for the one that's number 1. This one and this one. Token 2, 0 would then be this. Token 2, 2 would be this. Token 3, 0 this. Token 3, 2 this. So on and so forth. So I'm basically ignoring token 1, 1 and 2, 1 and 3, 1. So that's where our texture coordinate would be. But that's the texture index. In here, we'd have to do the same thing here. So for the normal list, we're fetching this. You just have to add 1 so that the function add vertex would not take 1 point in one vector. Or, yeah, basically, yeah. But instead, it would take 1 point, one vector, and then another point, and just use the first two. So inside this, where we have add vertex, it takes a position and a normal. It actually takes UV here, but it equals none. We would add that. So then we'd say the vertex array, number mesh ID, we add to this list of floating points. Behind this, we would probably just have to do uv.x, uv.y, and we'd have that, right? And then we'd have to do, change the draw function so that it calls here set attribute buffers with UV that we made earlier, so on and so forth. So we can just read the UV coordinates as well in the same way that the position and normal are being read now. We can send them in there and then they should go out. The other thing that we need to look at then is inside this object file, there's also a material file. So we have these different materials. You'll just have to look at what those materials look at once you add a texture. Because if you add a texture, this material will probably have a file location of that texture, and it'll save the file along with it, and so on and so forth. So you're going to have to make sure that the file is in the correct place, that this file location is read, and that's part of your material, and you send that along with it. So that's something you can figure out. It's a bit of programming, but it's not more complex than what we've already been doing with the sphere. So what else is interesting? We've done sphere texturing. We've done the sphere optimizing. We've taken the model and rendered that. Is there anything in particular that you're interested in seeing? Just trying to remember if there's something important that we haven't looked at, like regarding these things. There's a lot of complexity in this, and there's a lot of complexity in the code. which is the main reason that I'm going through this with you now and that I gave you the code to the actual file loading, is because even though the concepts are something that I want you to learn and understand, just the complexity of the code sometimes, would take so much time for you to actually go through that it'd take away from the fun and stuff you could do with the rest of your assignment if you're just working on this. So yeah, I'm just trying to remember if there's something cool, short that we can stick in here. One thing kind of been thinking about is if we could just do like a cylindrical texture map on an object, but maybe that'd take a little bit too long. I'll think about it before next Monday if we have time, and if anyone is interested, I can take a whiteboard session or something like that and explain it, because that's interesting as well. Because what the sphere is, the sphere texture map, is really not what's called a spherical texture map, but a cylindrical texture map, as if you're just going kind of around in circles. You're going from the bottom to the top, and in every location you're kind of pointing a vector away in different directions from that kind of central axis, that vertical central axis. And you're saying, if I imagine the texture were a cylinder wrapped around this, what coordinates would I be pointing at? So the y coordinates are just the height, where you are from kind of the South Pole and up to the North Pole. But the x coordinates you can kind of get by taking a vector with a cosine sine of that, and you can see where would I point in this texture map with this particular vertex. So you can take an imagined line to the center of the model, then you can take the cosine sine through each vertex from that line, and that will give you where you should hit the texture map, as if you just cylindrically wrap it around and then just push it towards the model. So that's a way to actually make a texture map rather than read it from UV coordinates in a file. These kinds of things. If you're interested in better explanations, talk to me. We can do more of this in code later on. But I think I'll leave it here for now to not add too much complex things, right? I always feel like I'm forgetting something, but I feel this is pretty cool at this moment. What would be super cool would be to go back in here, add this code again. So now we're working with the optisphere. Okay, so a bunch of texture mapped spheres. Even more interesting would be using a texture map that works on it, so we can steal this here, stick it in here, see what happens. Whoa! I stole it from the wrong place, didn't I? This is the one I wanted. That'd be great. Like so, there. And with all of this, well, our frame rate went a bit down, but it's still over 40 on my laptop while streaming this video, rendering and streaming this video. So, no, say we're still pretty good. All of these spheres, again, are, I think, 24 stacks by 48 slices, right?
What happens if you lower that number considerably?
Let's see. I just completely lost everything here. Like down to something like 612. I'm hoping that our current specular lighting in the shader should actually make the surface itself pretty nice. So the only thing really showing that this isn't a smooth surface are the edges, are kind of the silhouette of it. So you can obviously see.
The frame rate got down.
Wait, what? Yes, it did. That tells us that something else is the bottleneck here than the vertex count, at least. No, the bigger bottleneck anyway would be, well, once we have the vertex, kind of all that vertex reading gone out of the system. We're not sending the vertices from one memory location in one CPU to another memory location for another CPU. We're just storing it on the GPU the whole time. Once we've got that out of the way, then the per vertex calculations are really minimal. So the main bottleneck here is still the per fragment calculations. Well, it's back to 40 here. So you can see if I go in closer, the frame rate goes down because we're writing more pixels, because it's filling better out. We're still drawing the same vertices. We've got higher frame rate. So we've basically removed the vertex count as our main bottleneck. Instead, our bottleneck is obviously, the fragment shader, and there we're doing the texturing and some multiplications and stuff. So yeah, even lower, just to see what it looks like. And it doesn't. This number doesn't have to be double the other one. It just feels right to me to have it that way. I don't know, 2 stacks. Doesn't that? It'll end up a cube, right? Yeah. It still works, but it's a cube. It's interesting to see this one. You can see how, this is just a single triangle here. But you can still see how the specularity is so much more pretty now than it was earlier. After I normalized it and did the calculations properly, rather than allowing them to be kind of approximations, you got this perfect specular spot there, even if it's just somewhere on the middle of a triangle. So yeah, even lower. I don't think that we can. Well, 3 might work. 2 stacks, 3 slices. Yeah, now the pyramids are like triangular at the base as well. I don't think we can go lower than this without it, becoming something that isn't an enclosed model. But I'm actually happy this works. I'm pretty proud of having made the sphere building robust enough to handle this. So at this point, kind of looking at it this closely, we're at 37 frames, 38 frames per second. Back away, it goes up. If we take this into the ridiculous the other way, let's say 128, 256. This is an insane amount of vertices. Not much change to the frame rate. Well, yes, there is change to the frame rate, but still, it went from around 36 when we were up close to down to 20 something. We go further away. Okay, so it did affect the frame rate, but the vertex count is affecting the frame rate a lot less than we might expect. So just the amount of fill and the amount of pixels that we need to render is affecting this frame rate much more. Should take the near plane closer at this point. Set perspective, near plane of 0.5, let's say near plane of 0.1. I'm going to see if this is also somewhere else. Okay, and we can get closer just to see. Did I not save? It takes a longer time to load the spheres though, when we have this many. And obviously we're just storing the vertex sets for these once. So we should be able to go in closer now without it starting to clip. So this is pretty smooth. We can also kind of try to see the surface of it And you can see with this many, this is hard. With this many polygons in it, you can see like along the surface here, we're not seeing these jagged edges along the surface because we have like it's a really good approximation of a circle in both ways. Is this not the coolest graphics program?